going to look at a inductor in a circuit. So here we can see we have this little inductor here. It tells us it's about 8.2 millihenries, and I'm going to hook up a power supply to it. So we're just going to do a simple RL circuit. You'll notice that I could have hooked up a resistance here, but I did not, because the inductor itself is not ideal, and because it's not ideal, that means it has an internal resistance. And our time constant for the RL circuit is L on top and R on the bottom. So if I put another resistor on here, it's going to increase our resistance even further and make the time shorter. Speaking of the time, if we know the resistance and the inductance, then we can simply calculate the time constant. In this case, it tells us the inductance, and we'll check to see how accurate that is, but we have no idea what the resistance is. So what we're going to do is I'm going to drive the circuit with a kind of a square wave. It'll start at 0 volts, and then it'll go up to 1 volt, and then go back down to 0 volts. And I'm just going to have it repeat. That way we can see what happens as the current switches on and off. And we know that when the current comes on, the inductor will try to resist that and have this back EMF against it, and then we will see when it turns off that it will try to support the current and make it keep going. So in that case, it'll have an EMF but in the opposite direction. So we've got this guy here, but I don't have anything hooked up, so I'm going to go ahead and hook up the volt sensor and the current sensor. Okay, so I'm going to go ahead and hit the record button here, and so it's doing its thing, it's oscillating back and forth, and you're like, okay, cool. So right now I don't have a high enough sampling rate, so I'm only at 20 hertz. So I'm going to crank this guy up actually as high as it can go, which is 1 kilohertz or 1,000 samples per second. So let me do it again. And you'll notice that we get the same data, but now we have a couple of data points here. And looking at the voltage, let's try to zoom in a little bit on this voltage here so we can see what's going on. You can see that indeed there is a bit of a cycling going on. And you can see, there we go, that's better, that it doesn't just start, it doesn't just go to the peak thing here. So now we're starting to see a little bit of, peaked up, and then it pushed back against it and all that. So it's like, oh, we got some back EMF and all this stuff in here. So, but you'll notice that this time is incredibly small, right? And it turns out that I would like more than 1,000 samples per second, but this is what we got. So because we have a resistor in series with this inductor, we can find out the resistance, and we'll go ahead and use our graphs to find the inductance as well as the resistance in the circuit here. So I'm going to go ahead and zoom in on the interesting bits here for the current graph as well. So let's, there we go. A little bit more interesting, but you'll see that even though it is, doing exactly like we talked about in theory, it's incredibly fast. Like, look at that curve there. So let's go ahead and take some measurements. So we can think about the steady state of the circuit, and then the steady state where the current, the inductors stop misbehaving, you have current flowing. In that state, the inductor basically acts like a wire, and so we would only have the inherent resistance of the circuit. So here we can see, we have a voltage of 0.85 volts, and we can see in the steady state, so we'll go to the same time, so 0.655 just for fun. There we go, 0.655. So we have a voltage of 0.85 amps and a current of 0.158 amps. So we can use that to calculate the resistance of the circuit. So in this case, it should be basically just the resistance of the coil itself. Now, technically the wires I'm using will have resistance as well. And normally we talked about how we can just ignore the resistance of wires. Well, in this case, the only thing hooked up is wires. I mean, the inductor is just a wire, and the wires I'm using to drive this, connect everything, they have their own resistance. So all of this is going to add together. So they're all in series, so we're just going to do it as one resistance, and we'll blame it all on the inductor for now, and we'll see how accurate that is. So to calculate the resistance of this inductor, we'll just use Ohm's law, so V equals IR. So resistance would just equal voltage divided by current. So we've got a voltage here of 0.85, and we'll divide that by the current of 0.158. And so we get a resistance of about 5.37 ohms. Now I'm going to write that down for later, about 5.4. So here we are. We can just look at this and we say this is the equation we derived for an LR circuit. So remember, we talked about the circuit being a battery that was in series with an inductor and a resistor. So we can just draw that out real quick just to make sure we're being explicit. There we go. And so this is the formula that we derived for using Kirchhoff's loop rule for the current. And so that was the current at any time is I max times 1 minus e to the negative t over tau. So in order to do this, I want to solve this for the inductance, right? So we figured out our resistance. We calculated that from the steady state conditions as 5.37 ohms. Okay, cool. So we know the resistance, so we plug that in here. If we pick a particular time that it's been on, we can get our time there. We're going to solve this for our inductance. Those are constants. So I max, that's something we actually already have. I max from the data that we got earlier that we used to calculate Ohm's law was 0.158 amps, right? And just for the sake of argument, we got our voltages 0.85 volts, I believe. So this was our max, right? This is I max. Okay, so we know that, and so then we just need a current. So we need a current at some time t, and then we'll take that t and plug it in here, and we'll be able to solve for L. Not a bad deal. So let's go back to our data. All right, we're back here looking at the data. So now what we need is some data points. We know what the maximum is, so we need it at some certain time. Since I've just have this thing running here, it's probably going to be easiest to start from here, and we'll do a little delta function at some moment in the future. I can really pick any. I'm going to kind of pick one that's up a little bit. So here we go. This is our initial data point here. Ooh. There we go. There's our initial, there's our final data point, and then we have our deltas. Okay, so we've got the data written right here. This is all of our data points, actually more than we need. And so we can come in here and start plugging in. So for I of t at 3 seconds was 0.137 amps. And our I max we said was 0.158 amps. I'm going to do 1 minus e to the negative t. Let's go ahead and put r in there. Oh, I already should be plugging in stuff here for t and r. Okay, back up. So, negative here. So for r we have 5.37 ohms. And then t is, what, oh, 3. I don't know why I said 3 seconds. It's 0.003, very different than 3 seconds. And all of that's going to be divided by our inductance L, which we're going to look for. Okay, so the obvious first step is we're going to divide both sides by 0.158. 158 amps. Divide that guy out. So we'll have 1 minus e to the negative. I'll go ahead and multiply that while we're doing stuff here, make this a little bit simpler. So let me bring up our handy calculator again. So, all right, so with our calculator, we've got, so 0.137 divided by 0.158. So we're getting about 0.867, sure. No units on that, they canceled. And then we'll also do the 5.37 times our time of 0.003. So 0.01611, sure, why not? This would be ohm seconds. And then all of that is divided by L, which is not great. Okay, so I'll subtract 1 from both sides. So we get, I guess we'll just do this explicitly. What did I have? 0.867 minus 1. So negative 0.133 equals negative e to the negative 0.01611 ohm seconds divided by L. So obviously these negatives cancel. I'll take the natural log of both sides. Let's see if we can do a little natural log going in here. Oh yeah, we got natural log. So we'll say, I believe we have to do 0.133. And so give me the natural log of that. So that gives us a negative 2. It's basically just negative 2. I'll write decimals to satisfy people. Natural log of that's gone, so negative 0.01611 ohm seconds divided by L. So the negatives are gone now. So in order to find this, I'll multiply both sides by L and divide by 2.17. So that would be 0.01611 divided by 2. So this would be ohm seconds. 0.17. If you hadn't figured it out yet, ohm seconds is our inductance unit of henries. So let's just do that. So we've got 0.01611 divided by 2.017. Okay, so that gives us an inductance of 0.00798 whatever henries. Now, if we look back at our circuit, we remember that it had a given inductance of 8.2 millihenries. So if we convert this guy to millihenries, go 1, 2, 3. This would be 7.987 millihenries. That's a pretty good agreement there, actually. So we got about, I'd say that's about 8 millihenries. It says about 8.2, so that looks pretty good. So, okay, cool. We've got some good agreement here. Oh, ran off the camera there. So we got some pretty good agreement with what was going on. So the next thing I want to show you guys is I'm going to use this sensor here that can measure resistance and inductance and capacitance. And I'm just going to hook it up to our inductor to see what it says. I'm going to hook up this last cord here and then we'll see what the inductance is. So this meter is currently measuring inductance. So I plug it in, give it a second, it'll measure it. It says 8.12. So that's closer actually than our calculation. And it's pretty close to the given for the factory. So that's good. I wanted to show you all that. But also, this thing can measure resistance. So let's go ahead and switch it to not capacitance, but resistance. So what is the resistance? Oh, well, this says that the resistance is 5.6 ohms, and we got 5.37 off of our calculation. Again, it's in pretty good agreement. And the last thing I want to point out, zoom out, is you'll notice that the voltage actually goes negative, right? It went a little extra positive when we started and a little extra negative. Well, and that's from the EMF, the back EMF of the inductor itself. And so it makes sense that it goes backwards, because when we were measuring voltage, it was a positive drop, right? It should have been negative, but because of how I hooked it up, it was a positive drop. So when the inductor is the only thing in the circuit, essentially when we take the battery out, then the inductor pushes the voltage, it becomes the battery. So it looks like a negative now because the voltage is going to an opposite direction. But again, it's only for a split second, and if we had a better measurement device, we would be able to see that much more explicitly.